Hello everyone, welcome back. In this video, we are going to talk some more about elementary reactions. And this really is trying to pull things together and to move into chapter 14. And so I think as we go through this, you're going to find that chapter 13 and 14 are very connected. The big difference is chapter 14 are sort of applications of the basic concepts and ideas that we talked about in chapter 13. So let's get going. Okay, so in our last chapter, we talked about first order elementary reactions when we have A going to products. And to review this, we can say that the rate of the reaction can be written as the change in the concentration of A with respect to time. And because A is disappearing, we have a negative sign. And that is equal to K times the concentration of A, where K is a rate constant. And we can do this based off of the balanced reaction because we are working with an elementary step, meaning that we are not looking at some combined overall, but this is one step of a mechanism. So if we go from the differential rate law, the one that has the derivative in it, to the integrated rate law, following the approach that we used in the last chapter, where we integrate both sides, we combine our variables, we get that the integrated rate law can have either of these forms. We can have the exponential form, where the concentration of A at time t is equal to the initial concentration times e raised to the minus kt. Or we can take the natural log of both sides of that, do some algebra, and we can get what we call the linear form. Now, when we do this experimentally, what we would do is we would monitor the concentration of A with respect to time. And we can monitor that concentration in a lot of ways. We could use GC, we could use HPLC, IR, NMR, UV vis, fluorescence. All of these methods allow you to find the concentration. And what we would just need to do would be run that experiment at multiple times. And so if we graph the concentration versus time for a first order reaction, we get this exponential, and we can fit the exponential. This is a nonlinear fit. Now, something like Excel is not going to do this well. You will need to use a nonlinear fitting program, but with the right program, you can fit this data to a nonlinear fit, and from that fit, we can extract what the rate constant should be. Now, if we're stuck to using Excel or something a lot more basic, we will want to use the linearized form. And in that form, we plot the natural log of the concentration versus time, and our slope and our intercept have meaning for us, where the intercept is our initial concentration and our slope is the negative of the value of K. Now, we can derive this out for a second order elementary step where we have 2A reacting to form products. In that case, the differential rate law is given that the rate is equal to K times the concentration of A squared. If we integrate both sides, separating our variables like we did in the last chapter, we come to this integrated rate law, which is already the linear form. There is no exponential form here. And so to do this one, we would graph 1 over the concentration versus time, and we should get a line where our slope is equal to k and our intercept is equal to 1 over the concentration. So if you have data and you don't know what order of the reaction it fits, but you're pretty convinced that your data is, that your reaction that you're working on is simple enough that it will fit one of these elementary reactions, meaning that you are pretty confident that you aren't working with a complex mechanism. Instead, you're working with sort of a one-step reaction. And therefore, it should probably match one of these elementary reactions. So what you would do is you would measure your concentration of your species at lots of different times, and you would create 2 graphs. One that you would create would be the natural log of your concentration versus time, and the other would be 1 over your concentration versus time. And the question would be, which is more linear? In other words, which elementary reaction model fits your data better? The fit that is going to be the most linear, have the best R-squared value, have the smallest residuals, that is going to tell you that your experiment is likely to match either the first order or the second order elementary reaction. Okay, so really what we're doing is these elementary reactions are models, and what we can do is take experimental data and say, does this experimental data fit one of our models? The answer can be no. The answer can be that your experimental data is more complicated and does not fit either a first or a second order. So an example of something that might not fit a first or a second order would be a BiMolecular. So whenever we have A plus B going to form products, we can write the differential rate law as the rate is equal to K times the concentration of A times the concentration of B. It turns out that our integration for this is much more complicated, and we have to do some variable substitution, sort of U-sub style approaches in order to make this integral work. But if we do the fancy calculus, we get to an integrated rate law with this sort of complicated term. But this complicated expression for our integrated rate law is linear. And so even in this more complicated situation, we can make a graph of it. And our slope is related to our rate constant, and our intercept should be 0. So what you should see here is that if we can assume that something is an elementary step, we can write the differential rate law for it. And if we can write the differential rate law, we can integrate it and get to the integrated rate law. And that integrated rate law is a way for us to fit this data to a model. It's a model of how the reaction could be going. Now, some of these elementary reactions give us very complicated integrated rate laws, and going from the differential to the integrated is complicated. But, and I'm not going to expect you to do those. But if we can, then we can find a way to be able to identify if our reaction fits that model. Now, in a lot of reactions, in a lot of steps, we have reversible situations. Think about all of the times that we said that the acid HA plus water is in an equilibrium with H3O plus A minus. We haven't talked about this equilibrium in terms of rates yet. And so let's make sure that we understand this. So we can write, if we have this equilibrium reaction, A is in equilibrium with B. Really what this is saying is that we have two elementary reactions going on. We have A forming B, and we have B forming A. And so if we think about the change of A with respect to time, in our forward reaction, A is being used up, and so that is going to be negative K1 times A. But in our reverse reaction, A is being created based upon the rate K minus 1 times the concentration of B. And we can do the same thing with our rate of B. From the first reaction, B is being formed at a rate of K1 times A. And in the second one, B is being used up at K minus 1 times B. And those are the differentials. If I integrate these expressions, I get this very complicated exponential expression. But yet again, I could fit this. It would have a lot of fit parameters, but I could fit this, and I can get out terms for K1 and K minus 1 based upon the fit of the data that I use. Now, your textbook walks through the calculus to do this integral. I do not expect you to be able to do this. Concentration of B. So, what does this really mean? Well, at equilibrium, the definition of equilibrium is that the rate of the forward reaction is equal to the rate of the reverse reaction. That's not how you spell reverse. And these rates are not changing. And so we can say that K1 times the concentration of A minus K minus 1 times, is equal to 0. And so we can rearrange this, and we can find that our equilibrium constant is equal to our concentration of B over the concentration of A, which is also equal to the ratio of the rate constant for the forward reaction over the reverse reaction. And this right here is really the true definition of what is equilibrium. It really is that the rate of the forward reaction is equal to the rate of the reverse reaction. And we're going to use this as we work through this chapter with mechanisms.